Okay, welcome again. We can start with the second lecture. We have the pleasure to have Professor Raja Mittal from Johns Hopkins University. Just a word about Professor Mittal. He has his PhD at University of Illinois, and now is professor at the Department of Mechanical Engineering, and is the chief of the Flow Physics and Computational Labs Laboratory. And he is an expert in CFD at different levels, for example, for problems of swimming, flying, turbomachinery flows, and in particular for biomedical flows. He developed and used a lot of methods for CFD problem, like such as immersed boundary, large eddy simulation, and he is one of the pioneers in developing and studying cardiac blood dynamics, in particular with specific attention to turbulence and the interaction with the valve dynamics. Today, the talk of Professor Mittal is entitled Multiphysics Computational Modeling of Cardiac Flows from Fundamental Insights to Clinical Translation. Please, Raja, you can start. Thank you very much.
All right, thank you so much for the nice introduction, and thank you for having me speak at this conference. Looking forward to telling you a little bit about what we've been doing over the last 3 or 4 years. And all the work that I'm going to present today, almost all of it has been done in collaboration with Jung-Hee Seo, a colleague of mine, and my PhD student Shantanu Bailur. So, this is like preaching to the choir here, but as you've been seeing from a bunch of all these talks that have been given over the last day and a half, the heart provides a very amazing and rich substrate for examining all kinds of multiphysics computational modeling. And we have seen a number of talks on the electromechanics. There is also fluid structure interaction, which was the subject of the previous talk. Of course, the flow itself inside the heart is a very complex flow. It's a transitional flow. Typical Reynolds numbers range from a few hundred to a few thousand. So this is a range where, in fact, it's one of the most complex ranges for flows because it's neither laminar nor fully turbulent. So it has a very high degree of complexity, and vortex dynamics are very, very critical. So transitional flow is a feature of these types of problems. And then two things that I'm going to touch upon, actually talk quite a bit, is the connection between blood flow and coagulation biochemistry, something that the previous speaker actually talked about also. And then I might not get a chance to talk about this today in my talk today, but also the connection between blood flow and sounds, the heart sounds that are created. There's something that we've actually been focused on quite a bit. Today's talk, I'm going to focus primarily, you'll see our application of our methodology to fluid structure interaction, to transitional flow inside and the fluid dynamics, as well as the biochemistry and coagulation thrombogenesis. So the first kind of project, I'm going to talk about two projects today. The first project I'm going to talk about is left ventricular thrombosis. So this is the formation of blood clots in the left ventricle of the heart. So usually, so here's a little cartoon of the left ventricle, and as you've all seen, and this audience is very, very familiar, that there is a stroke, the left ventricle contracts and expands, and what is called the ejection fraction for a typical normal heart is about 55%. So one of the amazing things about a healthy heart is that despite the ejection fraction only being 55%, only 55% of the fluid is being ejected in any given cycle, the heart actually manages to ensure that there is no stasis inside the ventricle. And stasis is the key for thrombus formation. Wherever blood has an opportunity to be stagnant is a place where clots will start to form. And it's actually quite, like I said, it's quite amazing that despite this seemingly low ejection fraction, the human heart and mammalian hearts tend to be very good at avoiding stasis, and we, and along with other people, have worked on this. And hold on one second. Right. And we have kind of looked at the fluid dynamics of this. So this is some earlier simulations that we did, which showed that a normal heart is very good at washing out all of the recesses in the apical region of the left ventricle. And that's why a normal heart actually avoids blood stasis, and that's why, a healthy heart will never have a blood clot form inside it. But what happens is with different types of disease conditions, and especially myocardial infarction, the contraction of the heart becomes irregular. It might get diminished. The ejection fraction gets diminished. And in many cases, these left ventricles become prone to the formation of thrombosis. And here on the right, you're seeing the formation of a big clot at the apical region of the left ventricle. And so then the question becomes, oh, by the way, so what's the danger of this clot? Of course, the clot staying there is not dangerous, but the problem is that these clots are very mobile. They can be very unstable, and pieces can break off and lead to thromboembolic events. So that's really the danger of kind of this condition, is that it can lead to stroke and further myocardial infarction. So this is something that any cardiologist would want to avoid for their patients. And so if you want to treat patients for this left ventricular thrombosis, or to at least give them therapy that avoids this, then the first thing is to really try to stratify the risk as to which patients are prone to left ventricular thrombosis, and then only after that you can calibrate the therapy for those patients. So the typical way in which risk is defined for left ventricular thrombosis is primarily based on ejection fraction and also some understanding about the location of the infarct. So typically these ST elevated myocardial infarctions tend to be the major ones, lead to a lot of dysfunction in the myocardium. And so typically, if the ejection fraction is less than 30% and there's a certain type of size of infarct, then that patient is considered high risk for LVT. And those patients are usually put on a very aggressive mix of antithrombotic therapies, anticoagulants, antiplatelets, and blood thinners. Of course, the problem is that ejection fraction by itself is a very poor predictor of LVT risk. In fact, studies have shown, and we've done this a little bit ourselves, and I talk about this quite a bit, is here I'm going to talk about this cohort of patients in the first half of my talk. So what we did at Hopkins was that we had access to a very large database of patients and patient data. So from there, we extracted 75 patients where we had good quality imaging for all these patients. And these patients were equally partitioned into 3 groups. One was what we call the LVT group, which is the patients that actually showed a left ventricular thrombosis. The other one was the cardiomyopathy, the CMP group. And the cardiomyopathy group was a group of patients whose hearts seemed to be as badly compromised as those with the LVT, but they did not have a left ventricular thrombosis. And then the others were the normal group, which all had normal hearts. They came in for something else. They got checked. They came in for a suspected problem. Everything turned out to be okay, but in the end, we had all the imaging for them also. So now what you can see is that these 3 sets of cases are plotted against the ejection fraction. And you can see that ejection fraction would not be able to differentiate between these 2 groups at all. The average ejection fraction is about 24% for both groups. And so ejection fraction by itself would not be able to stratify among this group of 50 patients who would be prone to LVT and who would not. Also, of course, this one patient with 55% ejection fraction had LVT, and he would be missed if only ejection fraction was used primarily to stratify the risk. So bottom line is that there's quite a bit of evidence that this stratification of risk by LVT is highly overpredictive. It actually predicts a lot more people with the risk than there should be. In fact, there are some studies that show that almost this risk is being overpredicted by a factor of 10. So, many more people are getting this antithrombotic therapy than need to get it. And of course, there's a risk to antithrombotic therapy because this can lead to bleeding. And so that's a very, very significant risk. So more accurate stratification of this risk is kind of key to optimal management of these patients. So when we started working with these, with 2 cardiologists on this problem, the basic idea was that, can we use computational fluid dynamics and our understanding of fluid physics and coagulation chemistry to come up with a metric that would be better than the risk? So that'll be half of my talk. Also, the model approach, a lot of different problems, but in the context of the, can you see my screen? All right.
Okay, we wait just a minute to allow all the people to come back. And you have 25 minutes, Raja.
Mm-hmm.
So 15 plus 10, or as you prefer, in 15 minutes so you can conclude all your lecture. I think that all the people are here, so please, you can continue.
All right, so quickly, I apologize for the disruption, but I had a cable outage and thankfully it's fixed for now. So quickly back to my talk, I was talking about the numerical method. It's the immerse boundary method that we use, sharp interface. There's a lot of details you can find in these papers, but we can do very, very detailed, high resolution, direct numerical simulations and large eddy simulations. This is a patient-specific model. We have added a lot of other things to the code. The code can do incompressible, compressible, acoustics, convection, diffusion equation, fluid structure interaction, and active materials. And one thing that I will not get a chance to talk today too much is hard sound. So this is an example of the kind of simulations we can do of the propagation of hard sounds within the thorax. So very quick run through kind of the basic idea of coagulation and thrombosis. So when we talk about patients with myocardial infarction, we are talking about what is called the extrinsic or tissue factor pathway of coagulation, where basically there's a damaged wall, and the damaged wall releases a chemical called the tissue factor. And the tissue factor basically starts a chain reaction. It's a very complicated reaction. It can be simplified to whatever degree you want. But the bottom line is that the end product of the tissue factor pathway is the formation of a chemical called thrombin. And thrombin then initiates the next stage in the cascade. Thrombin does two things. Thrombin activates platelets, and also it converts fibrinogen into fibrin. And platelets and fibrin together bind together to form the clot, and the clot basically settles onto the wound and starts to help the wound heal. So that's the basic clotting cascade. It's supposed to work well for us to stop bleeding, but in the context of myocardial infarction and other cardiac diseases, it can actually lead to more problems. And by the way, this also activates the intrinsic pathway. Activated platelets themselves release thrombin, which again acts like a kind of reinforcement of the whole process. So this is kind of the chemistry that's underlying thrombogenesis. And what we have done in our code is basically take all these reactions and encoded them as a convection diffusion reaction equation. So not only can we solve the flow, we can also solve for the chemistry and also the different chemical species that are coming out. So it gives us an opportunity to actually get a little bit deeper beyond the fluid mechanics and look at the chemistry and the mixing and convection diffusion reaction physics. The pipeline, again, this is standard. Lots of groups are doing this. We can go from imaging, all kinds of imaging, to actually segment and construct our models. And that's the procedure. We're not driving this using muscle, but actually driving it by the movement of the wall itself as a kinematic boundary condition. So here's the results that we get from this. So this is the coupled chemofluidic modeling now of the left ventricle. This is actually a patient who has a very severe myocardial infarction. You can see that this bottom wall is not moving at all. So that entire wall has been damaged and it's become akinetic because of the infarct. And this is the location where the chemical is going to be released. The tissue factor is going to be released from this damaged wall. So this is the vortex structures, but we can go beyond that and start to look at now areas where you have higher concentration of thrombin and also of activated platelets and also deposited platelets. Here I'm showing you thrombin accumulation, and it's interesting to see that thrombin tends to accumulate much more in certain regions, and those would be the regions that would be more prone to the formation of a left ventricular thrombosis for this particular patient. And then we can also look at things like mixing and washout. How good is the ventricle in terms of mixing? And I just want to point out here is that there is one part of the ventricle where the jet actually is never able to penetrate and mix the flow. So this would be expected to be a region of stagnation and a region where thrombosis risk would be significant. So then we were working with this cardiologist, and they were asking us to come up with a new metric which would be clinically useful and clinically usable. And so that was a kind of a challenge for us as scientists. We tend to make things very, very complicated. But actually what is really useful is to make things as simple and easily clinically translatable, to be translated to clinic. So that was a little bit of a challenge in terms of our thinking. We tried a few different things like terms like near wall residence time, which is kind of well used in the fluid dynamics community to understand flow stagnation. But it turns out while near wall residence time can be obtained from simulations, it's not easy to obtain from any kind of imaging procedure. And that was the whole idea, was that we should come up with a metric that is also obtainable using standard of care imaging procedures that are used for these patients. So we kind of went back to the drawing board, and we had a little bit of an aha moment here. When we started looking at these kinds of animations, what we realized was that essentially risk would correlate by the distance that this jet penetrates and washes out in the ventricle. So if the jet penetrates all the way down to the length, to the apex and washes it out, then that should be a low risk situation, and vice versa. If the jet doesn't get all the way down, then it should be a high risk situation. So based on this, we are actually able to come up with a metric which can be obtained from current echocardiogram imaging. So this is kind of the typical imaging that's obtained right at the apex of right at the exit from the mitral valve. So this gives you the velocity. And basically what we said was that we came up with a metric we call E-wave propagation index, which is nothing but the distance traveled by the jet divided by the length of the ventricle. So that's basically the metric. If this metric is greater than 1, you have good washout. If you have less than 1, you have incomplete washout. And it turns out that the distance traveled by the jet can be obtained. Actually, it is already available from the echo. It's called the volume time integral. It's the velocity time integral. It's nothing but the time integral of the velocity, which is a length scale that tells you the length of the jet. So here was a new metric that kind of came out from our observations, from our simulation. And the question is, how well does this metric work? So if I can remind you, this was the data set, 75 patients, 25 patients in the LVT group, 25 patients in the cardiomyopathy group, and 25 patients in the normal group. And this is kind of the old classification. If the ejection fraction is less than 30%, then the patient is considered high risk. But notice that even these patients would fall in that category, and these patients actually did not develop a left ventricular thrombosis. So the question is, can this new metric actually differentiate the risk between these two categories quite well? And of course, it actually does quite well. So here is now the same patient data plotted against the E-wave propagation index. And as you can see, every single patient, including the patient who had the 55% ejection fraction, actually ends up with an E-wave propagation index less than or equal to 1, whereas the vast majority of the CMP group is above 1. So in fact, this index would tell us that these patients are not susceptible to left ventricular thrombosis, and all the normals range somewhere slightly above 1 all the way to 2.5. So this was kind of a very interesting exercise for us, where we went from very, very complex computational models, millions of grid points, all kinds of complexities, but all that complexity ultimately gave us an understanding which was very simple, which was that the depth of penetration of the jet might be the key factor here. So anyway, very, very complex back to very simple. And to some degree, I think I find that quite beautiful, that we managed to throw away all the complexity after we did the simulations and just get the insight from it and use that. Anyway, I'm going to switch to the second part of my talk, which is about transcatheter valves. And the previous keynote speaker did an excellent job introducing this topic. All I'll say is that these valves are becoming more and more popular. But one of the problems that's emerging for these valves is that 5 to 10% of the patients with these valves are experiencing early leaflet thrombosis. And while this thrombosis is subclinical, it doesn't really create any symptoms. But any development of thrombosis anywhere in the cardiovascular system is a bad news. And so the question is, can this be detected early enough so that the cardiologist can actually do some therapy and get rid of the thrombosis? So that was the whole idea behind the second part of my talk, which is coming up with some new technologies and ideas to detect reduced leaflet motion, which is what's caused by the movement, by the thrombosis on the leaflets causes a reduced leaflet motion. Question was, can we detect this early and do it in a proactive manner, not reactive, but proactive? So we've been pursuing this idea of actually using embedded sensors inside transcatheter valves. And as you all know that, sensors are getting smaller and smaller, they're getting more and more powerful, more data can be transmitted. And they're already kind of embedded sensors for monitoring the pressure inside the cardiovascular system. So taking this to the limit of really small sensors that would be less than 1 millimeter in size, can be embedded onto the stent frame of the TAV. And then question is, could something like this provide early warning of leaflet thrombosis? So that's the basic idea that we are exploring. Now, very quickly, I want to kind of talk about something here is that, and we're going to be using machine learning and statistical inference and things like that to understand these signals. One of the fundamental problems that all of us face when we are trying to apply any statistical inference to problems in medicine, especially diagnosis, is that if you want to do statistical inference, it's best to have a very balanced data set of positives and negatives. You want to have almost equal number of positives or negatives, not to bias the result. But the problem is that since doctors and medicine has gotten so good at actually so effective at treating people, it's very difficult to get positives. So for instance, if you look at problems like early stage aneurysms, very difficult to kind of find aneurysms that are untreated. Similarly, arterial stenosis, very difficult to find a patient who has stenosis in all different degrees and is not treated well. So, and where the stenosis is not kind of treated in some way or the other. And similarly with this early leaflet thrombosis, we have a problem that it's very difficult to find patients with this. It's very difficult to have a big enough data set of the positives because the incidence rate is so small, it's 5 to 10%. So this is, I think, where computational modeling, in silico models comes in, and we are really pushing this idea that in silico models is the way that you can create positives. That's the way you can create a large sample and use that to actually drive these kind of statistical inference models. So I'm going to talk about quickly, if I have the time, talk about two things that we are trying to do. So the whole idea is we're going to use computational models to create both healthy and thrombosed leaflets and valves, and then apply statistical learning to try and see what kind of sensors would need to be used, where would they be implanted, and what kind of signal analysis should be used with these sensors to ask two questions. One is, can we detect early leaflet thrombosis? And that, from a point of view of machine learning, is a classification problem. And then the second thing, is it possible to even determine the degree of leaflet dysfunction? And that, to some degree, becomes a regression problem. So I'll talk definitely about the first. I'll see if I have time for the second. So the way we are doing this is, of course, we have computational models. We have CT scans that we can use. We have a patient cohort of about a dozen patients that we are hoping to use. But we decided to step back and actually look at a much simpler model, a much more canonical model, which can be manipulated much more easily, is faster in terms of computation, and helps us to actually develop our insight that we can then apply to CT-based patient-specific models. So so the model is very simple. It's a very simple, relatively simple geometry. And we have chosen a leaflet, a fluid structure interaction, a leaflet model, a dynamical model, which is also kind of interesting and simple. It only consists of two parameters. So this is the model for every leaflet. There is a mass of the leaflet and there is elasticity of the leaflet. So we can actually manipulate the mass and the elasticity to create all kinds of situations. Simple, normal leaflets, thick leaflets, stiff leaflets. So we can actually tweak that in any way we can. So it's a very quick way of actually coming up with a very large class of healthy and diseased leaflet and valves. So, and this is the simple kind of inflow profile that we're using right now. So here is a sample result for a healthy case on the left. In the middle is a case where one leaflet is thrombosed, so RL reduced leaflet 1, and then the other one, which is reduced leaflet 2, where 2 leaflets are thrombosed. And you can see at the bottom the kind of movement that we get from this fluid structure interaction model. And so now we have a nice way of actually creating all kinds of cases for applying for the application of statistical learning. Just to tell you that we are interested in detecting very, very early thrombosis where the valve is actually not really functionally stenosed at all. So in fact, you can see on the left is that all these valves are way above the mild stenosis. So they are nowhere even close to moderate and severe. So this is that stage where we want to detect the problem. We want to detect it early. And in fact, for all these cases, the pressure gradient across the valve is less than 5 millimeters. So it's not something that's easy to pick. And certainly the patient would not be feeling any symptoms at this stage. I'll skip this. So how do we do this? So we are getting a bunch. So we have decided a certain arrangement of sensors. I won't talk about that, how we got that location, but they're kind of optimized based on the data. And so we have here, I'm going to talk about a sensor arrangement where you have 6 sensors, 1 sensor pair for each leaflet. The lower sensor is located just behind the leaflet, and the upper sensor, you can imagine, is located up on the stent frame, where the stent actually almost comes close to the lumen. So we have 3 pairs, presumably each pair is for 1 leaflet. So that's the basic idea, and we're going to look at the pressure difference across each pair. And basic idea behind classification is no different from the classic problem of detecting pictures of cats and differentiating them from pictures of dogs. Here, instead of cats and dogs, we have leaflets that are working and leaflets that are not working properly. And we apply the same kind of ideas of basically taking data, centering, normalization, feature attraction using principal component analysis. And then we can actually start to look at these various cases in the feature space. And you can see already that the red leaflets, healthy leaflets, actually segregate in one part of the feature space, and the reduced leaflets actually segregate separately, not all together, but they're at least far away from the healthy cases. So this is just 3 cases that just as a sample. But of course, what we have done is now gone beyond that. So we have a total now of about 21 simulations, which is 63 leaflets, sorry, 28 simulations. And we divide them into testing, training, and testing cohorts. So 21 for development and training, and then 7 for testing. So this is kind of the typical way things are done. And again, the question that we are trying to ask is that, can we detect, first of all, can we detect leaflet thrombosis from the fact that the leaflet with thrombosis is not moving as much as the other leaflets? And then can we determine the degree of leaflet dysfunction? So that's the second thing. So I'll skip this. This is, you know, these details, none of this is new. This is all well known in the literature in terms of classification and regression in machine learning. But just point out that for classification, we're going to use linear discriminant analysis, which is a very nice way of looking at the data in just the right angle in feature space that you can maximize difference between classes. And the regression is going to be using the classical kind of sigmoidal type of regression fit to try and obtain some correlations. You know, development consists of training and validation. And one of the things that we need to figure out is that when we do this PCA analysis, there's a sweet spot between using too little information and too much information, underfitting and overfitting. And the way you go about figuring that out is by doing validation. So this is a nice validation exercise where basically it tells you that you can minimize the classification error if you use something like 8 PCA modes. And then out here for the regression, of course, regression requires more information. You need about 18 PCA modes from the data to be able to get the best. Now you can see though that the minima are quite shallow, and you could reduce or increase these modes and not have a very, very significant effect on the analysis. But still, this is a nice way to actually figure out how many modes should be chosen. And then here is kind of the punchline. So this is for the 28. So we have 28 cases. 21 were used for training, and 7 were used for testing. And this is the discrimination index versus the number of leaflets. And basically, I'll draw your attention to the reduced leaflet, the tests, the blue and the orange. And you can see that the blue and the orange are nicely segregated on the 2 sides of the threshold that is determined from the training. So at least in this small cohort study, we get almost perfect classification in terms of leaflet movement, healthy versus reduced leaflet motion. Of course, this is a small data set, so I think this is a little too optimistic. Regression was the other thing, was that can we detect the degree of reduced leaflet motion? And quite interestingly, we can. So again, the blue is the training data. there's a prediction versus the actual degree of opening. And you can see that, in fact, the R square for the testing is also 0.83. So we get very good correlation in terms of being able to predict how bad the leaflet dysfunction is. So it seems quite, I think, promising. And we are now moving to, of course, patient-specific models. We have a small cohort of about a dozen patients, and we're going to apply these kind of in silico training and testing of these hypothetical sensors on the TAVR valve to see if we can actually detect reduced leaflet motion in these much more complicated cases. So I think maybe I'm still on time. So I'll stop right there, and just acknowledgements for the thrombosis work, and in addition to Jung Hee, my colleague, Richard George, cardiologist, Thura, cardiologist, they were essential to the work. And then on the transcatheter valve, we have a bunch of people working from students, colleagues, collaborators, Lakshmi Dasi at Georgia Tech, and then my cardiology colleagues here at Johns Hopkins, John Risar and Stefano Skenna. So with that, I'll stop right there and be happy to take some questions.
Thank you. Thank you very much, Raja, for this wonderful talk. We have time for questions, so let's see if in the chat or if there are any raised hand.
I think people are already drinking coffee.
Yes, of course. If there are no, I have a curiosity. If there are no other.
There is a question from the chat.
Okay. Thanks for the amazing talk from Cristobal Rodero. Did you try to disaggregate the data for the classification regression analysis? If so, did you find any difference with respect to analyze all the cases together?
So of course in our simple model of the aorta, there is no sex differences at all. It's a very generic model based on some aggregate dimensions of the aorta in adults. With the clinical study, the patient study that we are doing, we have about a dozen patients, and I think the inclusion criteria was to have equal number of male and female patients. Now that said, I think 12 patients is probably not going to be significant to give any kind of discrimination between sex-related differences. So I think that will have to, that question will have to be answered once we have a lot more data.
Okay, we have a question from Paolo Zunino. He's here.
Hello, thank you for the inspiring talk. I have a curiosity about the first part of the talk, in particular the, let's say, CFD analysis of the heart. And my question is about the trabeculae, so this protruding little muscle. So did you ever consider modeling these objects, these muscles, and what do you think would be their effect?
Yeah,
in the
yeah, that's a very interesting question. So in fact, back in 2017, we published an entire paper just looking at the effect of trabeculae on mixing and stasis. So it's the conclusion that we had, and that conclusion I think has been kind of shared by other studies that have been done afterwards, is that the trabeculae actually help with the mixing inside the ventricle, and they minimize stasis. They produce all kinds of additional vortex structures as the flow goes around them. And the trabeculae are not static, they're dynamic. There's little holes and recesses that open and close. They're almost like mini ventricles on the walls of the ventricle. And so all of that actually is a beautiful design, I think, from evolution to try and maximize washout and mixing in the ventricle. Now, in terms of adding those to our simulations, it turns out to resolve those in every simulation is extremely difficult, but you will see that at least the larger trabeculae are actually included in some of the DNS that we did. So let me actually show you. You'll see a little sense of, not this one. 1 second, sorry, this one. So you can see right here in this simulation that there is a high level of kind of detail to the luminal wall. So we have all kinds of undulations, but we don't have all the protruding details of the ventricles. It's just nearly impossible. This simulation was about, I would say, somewhere between 20 to 24 million mesh points. If we were to try and resolve the trabeculae correctly, we would need about 100 million mesh points. But if you're interested in this, there's a study that we published 3 or 4 years ago that actually compares with and without trabeculae the same ventricle.
Thank you very much.
Okay, we can thank again Professor Mittal, and in a couple of minutes we can...
Christian, there is a question from Professor Dussel if there is time.
From Professor Dussel.
Yes,
yes.
only if there is time. I mean, there was this time.
Yes, yes. Okay,
Yeah?
okay. Please, please.
Is there some time? So yeah. So thank you very much. And I was very impressed about this setting up a database for machine learning with simulated cases. And my question is, how would you choose the distribution of cases in the sense of mild cases, severe cases, healthy cases? Would you say that all these classes have to have the same number of cases in your training data set, or would you better choose a natural distribution, how often these cases show up in the hospital?
Yeah, that's a great question. So I think for the in terms of mild versus severe, our entire project right now is about mild stenosis, where there's no symptoms at all. The pressure drop is less than 10 millimeters of mercury. So we definitely want to not deal with severe cases. By severe cases, patient is already symptomatic, cardiologist can take care of that. We are trying to capture this very, very early. In terms of kind of how to segregate those cases, so the initial idea was that with these simple models of the canonical models, we wanted to play around with what is the range of pressures, distributions, and fluid dynamics that is created as the leaflets start to become more and more lazy. The plan is that to take patient-specific data, so we'll have these 12 patients right now. For each patient, we're going to create 10, 15, 20 additional cases by changing just a little bit of variation. So that's how we are planning to grow our database. Is everything will be based on some initial patient, and then we morph that, we tweak that geometry and the properties.
I kind of augmented data set. So
yes.
Yeah. That's
almost like augmented reality.
Yeah. Thank you.